So we've defined the Kolmogorov complexity of a string with respect to specific Turing machines. We've proven that there are optimal machines, which essentially minimize the complexity of all binary strings. And we've explored this definition with a couple lemmas. I now want to get back to the fundamental theorems, the fundamental properties of Kolmogorov complexity that really provide the foundation of the field. The next pillar that we're going to talk about are the fact that most strings are random. Okay. We begin with the definition. We say that a string, a finite binary string, is C random or C incompressible if the complexity of that string is at least the length of that string minus C. We saw previously that the complexity of any string is at most its length plus a constant. The C incompressible strings are where there's a partial converse, where they're lower bounded by their length minus some constant, minus C. Okay. So the second pillar of Kolmogorov complexity, the second fundamental result that we'll explore, is that in some sense, most strings are random, are C random. So for every natural number, there are at least 2 to the n times 1 minus 2 to the negative C plus 1 strings of length n which are C random. Okay, so before we get into the proof, I want to mention a couple corollaries of this. So, for example, more than half of all strings of length n satisfy C of x is greater than or equal to n minus 1. So almost half of all strings of length n are 1 random or 1 incompressible. Even more than that, for every length n, there are strings of length n such that the complexity of x is greater than or equal to its length. So regardless of what what length string you want, we know for a fact that there's at least one string of that length whose complexity is at least n. Okay, so back to the theorem at hand. The proof of this theorem is essentially just a counting argument, where you're going to count the number of inputs and arrive at our conclusion. So the number of strings pi of length strictly less than n minus c is the sum from I is equal to 0 to n minus c minus 1, summing over all the strings of this length. And if you calculate this out, the sum is equal to 2 to the negative, or sorry, 2 to the n minus c plus 1 minus 1. So that's how many strings there are of length strictly less than n minus c. Sorry. So the number of strings pi of length strictly less than n minus c is equal to 2 to the n minus c minus 1 plus 1 minus 1, which is just 2 to the n minus c minus 1. Therefore, the number of strings x such that the complexity of x is less than n minus c. So if you take any string x whose complexity is less than n minus c, it must correspond to at least one of these strings pi, one of these inputs. And so this is at most what we calculated, 2 to the n minus c minus 1. So there are at most this many strings that are C compressible. If we subtract the total number of strings of length n, so we take the total number of strings of length n minus all the strings which are C compressible, we get that there are at least 2 to the n times 1 minus 2 to the negative c plus 1 many strings that are C incompressible or C random. And the proof is complete. Okay. Again, this second pillar, this fundamental result, is that if you were to choose a binary string randomly out of a hat, so take the set of all binary strings of some length n and draw it randomly out of hat, with high probability, you're going to find a string which is very incompressible, is C incompressible. Okay. The last pillar, the last fundamental result of Kolmogorov complexity is that the complexity function, or the set of random strings, is undecidable. In fact, Kolmogorov complexity can be used to define sets and functions with really strange and wonderful properties, computability theoretic properties. We'll just focus on kind of the big one, undecidability, but it can be generalized to show really interesting objects from a computability theoretic standpoint. Okay. So first, we're going to define the set rand. So these are the set of strings whose complexity is at least their length. Okay, so the set of strings whose Kolmogorov complexity is at least the length of that string. We're going to call these strings random. One thing to note, by our previous theorem, rand, the set of random strings, is a non-empty set. So in particular, for every string, or for every length n, there is a string of that length whose complexity is at least n. Okay. So this set is not empty. Okay. A string at every length. And our last theorem, last fundamental property, is that this set is not decidable. The proof strategy we're going to use is a version of Berry's paradox. So what we're going to show is that if this were decidable, if this set were decidable, then we could compress a random string. Okay, so suppose for the sake of contradiction, that this set is decidable. We're going to show how this leads to our being able to compress a random string, which is a contradiction, which will prove our claim. So to arrive at our contradiction, the first thing we need to define is xn. So for every n, let xn be the first string of length n in rand. So we're getting the lexicographically first string of length n that's random, that's incompressible. Okay. And we're going to define the set A to be the set of all xn. So A contains the first string of every length in rand. Again, by our previous theorem on the number of of incompressible strings, this is non-empty. So once we have this set A, note that A is decidable. This follows because we assumed that rand is decidable. So if you have a decidable set, you can decide what is the first string in that set by simply enumerating in the standard order of strings. So A is decidable. And the cardinality of the subset of A of strings of length n is just equal to 1. So for any length n, A contains exactly one string of length n. Now we use our lemma 2, which said that if we had a decidable set, the complexity of any string of that set is related to the cardinality of the set of strings of length n plus a logarithm of n. Okay, so if you recall lemma 2, we're almost home free. So by lemma 2, the complexity of xn is at most two times the logarithm of n plus the logarithm of the cardinality of an plus some constant. Since the cardinality of an is 1, this is simply equal to 2 times the logarithm of n plus a constant. On the other hand, by our choice, by the definition of our set rand, the complexity of xn is at least n. In other words, we have the following inequality. But this is a contradiction. For all sufficiently large n. Okay. As long as n is large enough to render C inconsequential, this constant C, this is a contradiction. And we contradicted our initial assumption that rand is decidable. So the Kolmogorov complexity, the set of the random strings is not decidable. Before ending this lecture, I want to point out that much more is possible. It is possible to generalize this result to show that the set of strings, it's possible to generalize this result to arbitrary computable functions. So if you take the set of strings whose complexity is upper bounded by some computable function, so if you take rand f to be the set of strings whose complexity is upper bounded by if you take rand f to be the set of strings whose complexity is lower bounded by f of the length of x, where f is computable and monotonically increasing to infinity, you again get an undecidable set. Okay. In fact, you can even weaken the assumptions slightly to do away with monotonically increasing. So in other words, the complexity function is highly non-computable. And it has various other very interesting computability theoretic aspects, which might interest you in future lectures. Okay.